So anyways, we'll go over a little bit overview. So basically, what you want to do as a land developer is you buy some property that no one's built on, and because it's near the river, it's cheap, right? Because people think they can't develop on it. But if we can go and put in some fill, we can put some houses on it, shopping centers or whatever, and sell that land at a profit, right? We can then develop in an area that's maybe highly desirable, but it's in an area that might flood. So we want to figure out what the what the normal flood water surface elevation is, and then figure out how much can we allow it to rise. FEMA allows a maximum nationally is 1 foot, but it depends on the state also. State and certain municipalities will have regulations above that, or I should say below that or whatever. So for example, I'm from Wisconsin, so the regulatory agencies have set, or the state legislature set it to 1/100th of a foot rise, which is, what are you out there with a micrometer measuring that water surface elevation? Illinois allows 1/10 of a foot, Minnesota allows 2/10 of a foot, Iowa allows a foot. I don't know, I think Colorado allows a foot. Yeah, 1 foot.
No, half a foot.
Half a foot, okay, half a foot. Okay, so you can basically allow the water to rise up a half a foot by filling in, right? So if I make it rise more than that, they won't allow that. So we have to prove that, and we can do that by HEC-RAS. So to figure out where those encroachments are, where we're filling in, we're going to use the HEC-RAS software to estimate where that would be. Okay, there are other concerns you have to be worried about. You don't want to squeeze way down, right where you're at, because you're going to cause backwater further upstream. So some guy sitting in his house, and for 20 years he's lived there and everything's fine, and then all of a sudden next year you built your development downstream of him, and all of a sudden his backyard got filled in with water, or his basement or something, right? So you want to make sure you're looking far enough upstream so you're not changing that water surface. You're bringing that back down to the normal depth, what it was before. And then the other thing is you want to have a fairly uniform floodway. So when you encroach on this river, you don't want to have it very sinuous, and you don't want to have it squeezing down and then widening out and squeezing down and widening out. The idea is not to squeeze every last drop of water out of the floodplain into the floodway, but to try to at least to put something out there that FEMA will accept, and also something you can construct, because you want to have your property line, or at least the area you can develop on, fairly uniform, not where it's kind of doing some funky thing. All right, so that's what that is. So basically there's a step process there. We're going to compute the natural conditions. They call that a base flood profile. And then we're going to compute our encroachment, our floodway. And like I said, you can't, your maximum allowed rise in Colorado is half a foot. And you have to watch out. You can squeeze so much that the water surface elevation starts to drop below normal depth. What would that be indicating of? Anybody have any idea? What if my water surface starts going lower? That sounds good, right?
Increased velocity.
Increased velocity. But what's that telling you then? What's causing that probably? Supercritical flow. Yeah. So you got to watch your Froude number. Your Froude number, if it's an indication of if it's subcritical or supercritical flow. And there's a Froude equation you can look at it. I don't remember it. You'd have to look it up. But basically, if it's less than 1, you're subcritical flow. If it's near 1, you're getting close to critical depth. And critical depth is like when you're over a spillway. You remember how it passes through critical depth? And then when it's greater than 1, it's supercritical. And you don't want supercritical flow. For example, when you're doing bridge modeling, you want to be very cautious about modeling a bridge that has supercritical flow through it. Why would that be? Any ideas why we want to make certain that when we're analyzing a bridge, we're analyzing it for subcritical flow, not supercritical flow? Now, obviously, you could have some mountain in the stream here, and it's going to be supercritical flow. But let's say you squeeze that bridge down enough, and the flow passes through the bridge opening as supercritical flow, but upstream and downstream it's subcritical flow. You could imagine that, right? That could happen, right? Why would you want to be cautious not to have that happen? Trick question here. Well, it's got it. Let's assume that we go out there, we excavate. I used to run a bulldozer. That's why I'm hard of hearing. The first day I drove the bulldozer, I didn't have any ear protection. Back then, they frowned on it. You weren't a man, right? And I couldn't sleep that night. My ears were ringing all night. I said, what the hell's going on? And my boss said, you need to get some hearing protectors. He gave me some hearing protection. And back then, they were probably not very good. And so I've lost some of my hearing because of that. But so I've run a dozer, and you grade through there, and you can make it nice and smooth. So what's my Manning's value? Pretty low, right? It'd be pretty smooth through there. But over time, what happens? Especially up in Canada, things grow, right? Brush and debris shows up, and birds put nests in and all this kind of stuff. And all of a sudden, my Manning's value is no longer 0.035. It's like 0.06 or 0.1. So what happens when my Manning's value goes up? What happens to the water surface elevation? It'll slow down the water, right? The velocity will go down. So if I have the same amount of flow, well, less velocity, area's got to increase, right? So water surface is going to rise. So if I'm analyzing a bridge and it's flowing through supercritical, just a small change in Manning's value could make it switch to subcritical. And my water surface will go through a hydraulic jump, but eventually it will be subcritical through there. And my bridge analysis that I analyzed will be invalid. And then I've forgotten the lady's name at the end there. Yeah. She's going to have me in court. She's going to take me, cross-examine me in court, say, Mr. Mater, I understand you chose a Manning's value of 0.035, but as you can see from these pictures, we have a lot of debris and brush there. Why did you choose that value? Right? She's gonna have me in a sling, my rear end in a sling, right? So you want to be careful of that. The other thing is you want to choose Manning's values that are not what the current conditions are, but what you expect them to be in 10 or 20 years. Because you probably won't have guys out there mowing and taking out the debris and stuff. And then if you're a county engineer or if you're working in a highway department, what should you be worried about? Making sure your maintenance guys are out there taking out all the debris and stuff, like unlike in New Jersey where they come by every 30 years and say, oh, there's a tree there. Oh, that's nice, right? That'll help hold up the bridge. Okay. So we want to make sure that surcharge doesn't go down. We want to watch that true number. Okay. So we saw there's different values there. And like, for example, some communities, Tulsa, Oklahoma, we did Oklahoma City yesterday, but Tulsa, Oklahoma has also flooding issues. They basically say no rise. They've had so many flood conditions where Tulsa's been wiped out, they say you cannot encroach on the floodway. They've gone now and redeveloped that floodway, that floodplain, as undeveloped because they have no way to store that water and everything gets wiped out so much. They bought everybody out and reinstitute that river that runs through there as just a big floodplain. Okay, so this is an example of a project I worked on in West Virginia, and here we had to put, it's basically they make charcoal briquettes, and I guess that was owned by Clorox company. I didn't know that when we built that, but we had to come in with a levy. And in West Virginia, they're pretty lax, right? You can probably, I mean, if you look out there, I was there for about a couple weeks, and you go by the streams and they'll, when they're done with something, they just put it in the stream. So you drive by the streams and you see a refrigerator, or there's an old car stuck in the stream. Instead of taking it to the dump or whatever, they just drive it into the stream. So the regulations in West Virginia, hopefully no one's from West Virginia here, or just put my foot in my mouth. But they're pretty lax as far as regulations. So anyways, we put in 11 cross sections in there. We put in a levee to kind of prevent that from wiping out that plant. So how do we determine it? We're going to basically calculate the water surface profile for a known event. It's going to be the 100-year. We're also going to analyze the 500-year event, but we're not going to consider that in our encroachment analysis. We want to basically know where the 500-year limits are. We're going to use the 100-year flow values for performing the encroachment analysis. We're going to use what they call method number 4 to figure out where the approximate floodplain encroachment stations are located at. That means HEC-RAS is going to try to figure out, if I say I'm allowed a ½ foot rise, it's going to sit there and try to come up with a ½ foot rise. It's going to work on that. The problem with that method is it doesn't get the ½ foot rise. It'll go, 3/10 of a foot rise, it may go a foot rise. So you have to try several different, what you call targets. You try different profiles with different encroachment targets, and you try to iterate that process until you reach that allowable rise. And then when you're finally done with method 4, you save that, because you have to submit that. You duplicate that plan and use now what they call method 1, where you fine-tune the floodway. So when you use method 4, you might have a nice floodway analysis showing your ½ foot rise, but the water surface or the water profile or the river alignment might be jumping around. And FEMA won't like that. They'll say, can you go on and smooth this out to kind of clean this up? Because they don't want to publish FEMA maps that show the zigzag as it goes down the river. So then use method 1 and try to do the alignment along that floodway. The stream itself might be meandering, but the floodway will be running parallel to that, kind of nice and smooth. So we'll use method 1 to approximate that. Again, we can't go over that ½ foot. And usually that you never get to the value you're trying for. You're trying to get somewhere near that. Now in HEC-RAS you have this dialog box, and it's difficult to use because you actually have to have 3 dialogues open at the same time, and it's hard to remember where you're at. And we had a guy come to us and said, Chris, you should take this, this, and this and put it all in one and just work in that one dialog box. And so that's what we implemented. So I'm going to show you how that is. But anyways, there's an equal conveyance reduction that's required by FEMA. So you might get away with turning that off, but don't submit your studies to FEMA. They'll run us through something called CheckRAS. And CheckRAS is a program written for FEMA. And basically it does a bunch of quick analysis checks on your model to see whether or not you violated any of their rules. So rather than having someone manually check each of these items, they just run it through this computer software, and it kicks out a report and said, oh, this guy turned this on or turned this off, and that shouldn't be there. So it just instantly gets rejected and gets sent back to you. So you submitted your study to FEMA. You're sitting there waiting. 6 weeks pass by, it finally gets a rejection. So you want to make sure that you don't violate that. So you should download a program called CheckRAS. It's available on FEMA's website if you're submitting studies, and then run CheckRAS as well, and make sure certain it passes those requirements there. You can watch on YouTube. There's a CheckRAS video by FEMA that shows you how to operate that program. So if you're submitting anything to FEMA or to a floodway agency or something like that, someone who's in charge of regulating the floodway, make sure it passes through that, or it'll get rejected and you're down, a couple more months because you forgot to do that. Okay, so there's also another method where you can define offsets, where you can define a buffer zone around the main channel, so basically it will encroach up to the bank stations and stop. So depending where you define your bank stations can have a big impact. So if I come over to our model here, and let's just look at it in 2D here. If I go and look at my cross section, let's say right here, if I look at that section, I have my banks in here, right? So I could encroach up to that bank station. If I unfortunately put my bank stations further out, I can use my add bank station button here, and I say, okay, my bank station's here and here. Then it will encroach up to that point and stop. So as a modeler, you should be aware of that I want to make sure that I put my bank stations in where the channel is, and the channel is basically where there's no vegetation. That's kind of the stream channel. That's where the normal flow is occurring. Now here you're in Denver, so there's not a lot of vegetation, but you can still use some engineering judgment to say, okay, I want to put that bank station down in there where the normal flow conditions are, and map those right in there. Okay, so placement of your bank stations is important. Don't put them way out in the overbanks, or you'll find that it's like I'm squeezing, nothing's happening there, and it's because it says I'm right to the bank, I can't go any further. But there's an option to put a buffer on either side in case, you know, maybe the local community says we don't want you to encroach within 30 feet of the bank station. They might want to have an environmental corridor along there for wildlife or something like that. And then, all right, so I don't want to go over all this because this is kind of confusing, because this is if you're using HEC-RAS, and it's kind of a laborious process to do, and it's very easy to make a mistake and then ruin all your work, because there's no locks in the sense that you could be working on a model, you've got this lower section done, and you're working your way up the river, and then you say, oh, got to make a change here, and you change the wrong cross section, and you change one that you were finished with. There's no way to prevent you, software, from telling you that, and now you've just lost all your work. So if you don't save your work in the process, you can lose out on that. So, but anyways, we're going to look at method 4. So method 4, we're going to start out with method 4. We're going to come up with approximate encroachment station locations. We're going to define our target increase. In our case, as you're working in Colorado, it's going to be a 5/10 of a foot, right? Half a foot. We're going to make certain equal conveyances turned on. It is by default. And we're going to set different targets to kind of approach that. Then we're going to switch over to method 1, and we're going to fine tune it. We're going to place them in the exact spots. Okay. So method 4 basically says we define allowable rise, and the software tries to come up with encroachment stations. So I might ask for a half a foot, but it's not going to hit it. So I might ask for 3/10 of a foot, 7/10 of a foot, try different values and see which one came close. And you have to work your way from downstream to upstream. So I use what they call a scattergun approach. I try different targets. A scattergun is, anybody shoot ducks or geese or anything like that? Any hunters in here? I don't hunt, so don't accuse me of going out killing ducks or something. But would you use a rifle for going out duck hunting? Why would you not want to do that?
I'm not that good a shot.
Yeah, so you wouldn't hit it. You'd have to, that one little bullet would have to hit that duck. And most likely, if you hit him with that bullet, there would be nothing left of that duck, right? It'd be just gone, be a bunch of feathers, right? So if you use a shotgun, they use BBs, little tiny pellets. And when you shoot it out of a shotgun, you get, you know, these BBs spread out in a pattern, and hopefully one of them or a couple of them take down your duck. Now, we're not duck hunting here, but we're going to try several different shots and see, hopefully one of these pellets gets lucky. So I'm going to show you that in our exercise where we use a scattergun approach or a shotgun approach there. And so even though we ask for a 1 or half a foot rise, we're not going to hit it, but hopefully something will hit it for us. Okay. And then we go ahead, and when we're done, then we're going to go and turn off that option and switch over to method 1. And method 1, we specifically define the locations for it. Okay. And then we have to submit both. We have to submit our method 4 and our method 1. Okay. So special considerations here. You know, if they say a half a foot rise, it doesn't mean 0.51 feet. It means half a foot. If you're putting in a bridge structure, that can also cause problems, right? You'll have to go and converge back to a normal depth within a certain range there. So you may have some issues there you have to worry about. Uniformity of the floodway. You want to have a fairly uniform floodway through there. You don't want to have it squeezing down or widening out and squeezing down. So I kind of have a rule here, like don't go below 1 to 5 contraction or expansion in the floodway top width. So let's say I'm going 100 feet. I'm going to go 20 feet out. All right, that's like 20% there. Velocities, watch out your velocity. You don't want to go over 6 feet per second. They can flag you for that. So you want to, if you cause real high velocities, they're worried about little kids walking over and looking at the flood and putting their foot in and getting swept away, right? It's amazing. You see the news on TV or on the internet, and there's always someone in Alabama or Missouri or Georgia or whatever, and then you go out and examine the flood, think they can walk from somewhere, and you know, you read about how they're now missing somewhere. Want to watch that fruit number, right? Want to stay subcritical flow. Environmental buffer we talked about. Some modeling tips here. I think it's better if I just show you. Oh, some tricks here. hopefully there's no regulatory people in here, otherwise just plug your ears, right? One trick we can do is we can mark areas of ineffective flow. So if you had an area that is stagnating water, you would mark that as ineffective flow, right? This, in this case, would make reasonable sense, right? We go mark this as ineffective flow. And so this would, in normal flood conditions, this would be effectively carrying flow. If I do that, I don't have to prove to FEMA that that's part of my floodplain encroachment. I now have gained that land back. So look at your contours out there where your river is, and if you're a land developer or you're working for a land developer, those are areas you can quickly retain, get back with minimal amount of effort. So you can go in there and mark out those areas that are ineffective flow, and that will help. Another thing you can do is you can revise your flow links. So if we revise them to represent the direction of flow here, now in normal conditions it's going to flow down along this channel, right? But in real flow conditions it's not going to do that. It's going to short circuit. So we want to put in the flow links of what the flood would be. So we might have, if we're developing a model, we have to worry about the flow links. So we might have, for the 25-year flow or the 10-year flow, we might have different flow links than our 100-year flow. Unfortunately, in HEC-RAS, if you have one plan, you got one geometry, you have one flow length. So you might have to have a separate plan for your low flow conditions and one for your high flow conditions. So by revising the flow lengths, you can also reduce the water surface elevation, and that can also benefit your client. Okay, encroachments at bridges. So basically, you don't encroach in bridges. You just stop the encroachment before you get to the bridge. And that's it. Okay. So here's some graphical plots. So here's an example where we've encroached on both sides. So we've now gained this land back for our land developer. And so maybe your land developer only owns the area on the right-hand side, and he'll complain, well, he gave all that land to the guy on the other side of the river. It can't help it, right? That's equal reduction of conveyance. I got to reduce the amount of conveyance on both sides. Now, when you go and fine-tune it with method 1, those rules are off, right? There's no equal reduction now, so now you can kind of play the game. Okay, this is my guy over here. I'm going to give him a little bit more land, so I'm going to maybe put it a little bit more on this side, and hopefully the other guy on the other side of the river doesn't find out, or the regulatory guys don't find out, or that lady on the end doesn't take me to court, right? All right, so then there's a graphical plot. Let's go take a look at it here.
You're not going to typically submit your method 4 run.
You do.
You submit your method 4 run and your method 4
Yeah,
run?
you have to do both. You can probably try to submit your method 1, but if you got a guy on the ball, they have to run it through CheckRAS, so they'll have to have both. They require you to submit both. Because, you know, to a land developer, time is money. He takes out a loan from the bank, right, to buy this property. He wants to turn it around, right, make a quick profit. If you're hanging up with FEMA, you know, and it's like, well, I submitted a study to FEMA and they rejected it, I got to fix it again and run it again. You know, you might increase your billable hours to your client, but his time is burning too, right? So he's paying the bank on that interest. He wants to turn that around so he can develop that land before frost comes or whatever. So you want to kind of get it done the first time.
Well, can you give an example why you would use any of the other methods?
FEMA won't accept them. There's method 2, there's a method 3, there's a method 5. They won't accept those. So they will only accept method 4 and method 1. So this is kind of like programmers gone wild. You know, hey, let's put this in. Hey, let's put that in. Well, it's cool, but no one uses those, right? FEMA has enough problems just trying to get their web map service running, right? So now you send them all these models that have all these different options. They're going to have to know how to manage those. So they said, no, we're going to take method 4 and method 1. You have to do that. Okay. You can use those other methods to kind of figure out what's going on. So method 2 allows you to find an equal floodway. You can say, I'm going to make the floodway 100 feet all the way down, and it'll do that. And then you can say, okay, that worked, and then I could use that in my method 1, but you can't submit the method 2. You could use that to kind of analyze it more. You could use method 5 that uses energy instead of water surface elevation, and energy probably would have been a better way to calculate it, but FEMA doesn't look at that. They don't look at total energy, right? They look at just, and if you're doing bridge modeling, you want to look at total energy, right? Remember we talked about that yesterday? Why do we want to do that? There's a final exam. You guys know that, right?
That's as high as the water could get?
Right, right. If the water stopped, if I put a board in there, water's going to rise up total energy, right? It'll stop and pop right up.
I think urban drainage or the Mile High Flood District will look at energy.
Okay.
Put a cap on that too. So it's energy and water.
Okay.
It's half a foot for a year.
Okay, okay.
Just don't know that.
Yeah, the guys here in Denver are sharper than most, so you got to be careful there. Okay, let's go take a look at that then. So I have an example that I provided you guys. Let's go open it up. Unfortunately, it does not have a map view. So I'm going to go over to floodway modeling. It's one that comes with the Army Corps HEC-RAS software. So it's called Beaver Creek. So it's in, yeah, and I'm just going to work through it first. I'm going to work through it first, and you guys watch me, and then I'll have you guys go through it, okay? And this example, we're going to take a look at it here, and find it here under my folder. It's under number 5, floodway modeling, okay? So there's different plans in here. We're going to just stay with this one plan. And so we want to go look at our flow. So we're going to go over our steady flow data. And I'm only interested in the 100-year flow, right? So I would put a 500-year flow analysis in there as well. You're going to want to know where the 500-year floodplain is. I'm going to have to submit that. I don't know what about Denver, but FEMA's going to require that. But you don't encroach on the 500. You only encroach on the 100-year. And the 100-year flow, you got to come up with that, right? So you want to go and see if FEMA's already done a hydrology analysis so you know what the flows are, so you don't have to do that. Otherwise, you got to do the hydrology on it. And now, because we're civil engineers, I'm an engineer, everybody else is an engineer here, hopefully. We have job security because climate change is coming, right? And all of our flow values are going to change one way or the other, right? So we have job security. I'm going to take this, copy it, and paste it in this first row. And I'm going to call it my 100-year base, so I know what it is. That's going to be unencroached. That's going to be my natural conditions, right? And then I'm going to put in 3 different targets. I'm going to type in, watch this, guys. Otherwise you'll miss it. Remember, you want to see it again? Right? Target number 1, target number 2. Now in Excel you can create a series, and this has an Excel component in it. Just grab that series, pull it down. Guess what? Target number 3. Isn't that cool? Try that in HEC-RAS. You can do it. All right, we're going to go and pull that down, the same flow values, right? So the first profile is our natural conditions. Target 1, 2, and 3 is our scatter gun or shotgun, or you're trying different targets, right? You could put more in there, but I have trouble enough managing 3. So 3 is pretty good. For our downstream condition, we're typically tying in, you might be tying into an existing FEMA map. So you want to use their known water surface elevation there. You don't want to come up with some, you don't want to use normal depth. You want to, if you're tying into an existing FEMA map, you have to use their water surface elevation, the downstream end. So we're going to use water surface elevation for all of them. And this is my known water surface. And I'm going to allow, and let's assume we're not in Denver or Colorado. We'll say we're working in Nebraska, right? And don't take pot across the border. I heard you can get stopped by the state patrol and get thrown in jail. Is that true? I don't smoke pot, but is that true? Everybody's laughing. No, I know it happened to me. Okay. But let's assume we got a 1-foot rise there, so I'm going to carry that across. People say, "What's pot?" I don't know what that is.
Sorry, Oscar. I don't know what that smells like.
Okay, so we got a 1-foot rise there, right? Okay, so we're working in Nebraska. Okay, hit OK. That's right nearby, right? Yeah. Nebraska is right nearby. It's one of those states you drive through and it just keeps going and going and going forever. Mm-hmm. Okay, so I have a 1-foot rise defined for my different targets. All right, so I'm going to save this off. I'll just hit save so I don't lose my work. All right, so I'm going to call it Beaver Creek in there. We'll hit save. Saves it out, right? So we started out with a HEC-RAS model, pulled it in, and it's now a GeoHECRAS model. And I've changed my flow values. I'm going to go over to my analysis, and under floodplain encroachment, I'm going to choose floodplain encroachment options. And now just watch me, otherwise, if you try to follow with me, you're going to kind of like, what button did he click? I'm clicking on buttons. I don't know. What did you learn, Chris, or Bob, or whatever your name is, at the training? How's Chris' training? I don't know. I was just clicking a lot of buttons, right? You ever had a course like that? I taught courses at Autodesk, and I'd go take courses at Autodesk, and the instructors are, there's no handouts. You're just sitting there watching this guy click, 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 click. You know, there's like so many buttons you're clicking. Where is it? So this guy here wants me to come up with my tutorials. I'm going to send you the video at least. So we're going to floodplain encroachments. Everything's in one dialog box. Everything's all centralized in one. We just stay here. We don't go anywhere. Anybody used this before? Mm-hmm. Yes, you have. Okay. So in here, we're going to define our cross sections. You can see this is the downstream end. And if I scroll here through this is all my other sections all the way upstream. You can see I have 4 different profiles, right? I have my 100-year base profile that's unencroached. Notice there's no encroachment method available there. And then I have target 1, target 2, target 3, right? And then I can choose my encroachment method. Notice only method 4 and method 1 are available for us. Okay, and then it's going to compute for us the water surface change, the top width, right? We want a fairly uniform floodway through there. Our velocities, we want to keep it below 6 feet per second if we can. Our Froude number, we don't want to have it go over 1 or close to 1. We know we're getting in trouble. And also storage volume. Some locales say that if you're reducing storage volume, you have to replace it somewhere else. So this gives you an idea of how much volume is being lost by that encroachment. So basically, we're going to work, right now we're going to work in this area here down at the bottom. I'm going to choose target 1, and we're working for 1 foot rise, but I know 1 foot rise won't work. So I'm going to enter 0.8 of a foot. I'll say 0.8, and I'm going to click on assign. It'll go through all of my cross sections and assign that for target number 1. I'm going to choose target number 2 now. I'm going to ask for a 1 foot rise. Click on assign, and it's going to fill in my target 2. For target number 3, I bet you guys can guess what that one is, right? 1.2 foot rise, right? Click on assign, and it fills all that in. So we now have this done, all right? Now down below, there's our equal reduction. We don't change that. We leave that alone. Here's our buffer zones if we want that. I've never run into that, but that's in there. Here's where we're going to do some checking. Our maximum water surface rise. Okay, here you would enter, in Colorado, you'd enter 1/2 foot. We're going to put 1 foot in. Maximum velocity, 6 feet per second. So if it goes above that 1 foot or 1/2 foot, or goes above that maximum velocity of 6 feet per second, it'll color in the cell to point that out for you. So you know, like, uh-oh, I'm violating this rule. In the meantime, it's also going to go and calculate a flood map for us. We're going to see our flood map show up. All right, so I'm going to go and click on Analyze, and it's going to run my simulation in this dialog box. You can see the progress bar down at the bottom, and it's going to compute our results. So here we can see our allowable rise, and we can see upstream we're way above 1 foot, right? And we can see our velocities are above 6 feet per second. We can see our Froude numbers are looking okay, although this one's getting a little high. If it goes to 0.95 or higher, it'll color in as red. Now it also has plotted for us on our map view where the floodplain is. Now I don't have a terrain model, so it won't look nice. But it also then shows my floodway. Now the floodway is always drawn as a straight line because we don't have any understanding of what the floodway will look like. So we draw a straight line for you, and then you can use that curvilinear command that I showed you yesterday, or we'll do it again today, where you can kind of smooth the river out, make it look nice. So obviously I'm having some problems here. What am I having? I'm squeezing way too much at the downstream end, right? I'm squeezing too much, and what is that causing? It's causing additional backwater upstream. The downstream end is at the bottom of my screen here, so it's backwatering up the screen there. So we want to have a fairly uniform floodway. So let's assume that at cross-section number 2, that floodway that's shown there is approximately what we want all the way along our river. So if I look at cross-section number 2, I see my top width is about 480 feet. Everybody see that? But do I see it over here? I don't. I see this is way too much, right? So we're going to take this minimum value here, this 0.8. I'm going to make that my new maximum. So I'm going to right click on it, say copy, paste that in as my maximum. I'm going to put a value, let's say 0.2, and I'll split the difference. Let's say 0.4. And we're going to click on Analyze again. So we're basically using trial and error here, analyzing this process. So we're going to see if we get that. We're moving our shotgun a little bit, right? We're moving our targets. So we want 480 feet. So here we now are bracketing that. We want to bracket that target we're shooting for. We're shooting for 480 feet. We're a little bit low, a little bit high. That's good. We want to be able to. We want to interpolate, not extrapolate. So my target should be somewhere between there. So I'm going to take my 0.4, I'll copy that, paste that over here as my new maximum, split the difference, say 0.3. This is again another reason why I only put 3 of those encroachments targets in there, so it allows me to kind of bracket things. Let's go ahead and reanalyze this again. Hit Analyze. We're looking for 480 feet. Let's see how close we get. Well, we got 488. That's pretty close. For method 4, you don't want to fine tune it. You can spend hours on this, and it's just a waste of time. So just get it close enough, and that's good enough. So that 488 is pretty good. In fact, you can also see it on our plot down here. It's looking pretty close. It's a little bigger than the 480. It's 8 foot wider, but it's close enough. So let's assume that's good. So we want to basically take this same value and make it go in all of these entries. We want to have all these entries the same. Click on the Analyze button and just confirm that they're all. So now we basically moved our starting point from the downstream end to the next upstream section. We're kind of moving our way up that river. So 488 is good. Now in HEC-RAS, you could define that, say, okay, I'm done with that, and go on, work your way up the model and say, oh, I got to make this change, and you're not quite checking what you're working on, and all of a sudden you accidentally change this value. What did you just do? You blew away all your results because you don't remember what it was, because there's no way to remember it, right? You didn't save it, and so you're out of work. You got to start all over again. So what we have done, because I've done that, is we put a little lock button in there. Lock it, and now we can't actually change these. These are locked in. We can't. I can try typing in there, but it's grayed out. Okay, I'm finished with that one, right? I can lock it in position. So now we're starting again here. So we want 480 feet, and guess what? We got a free one, right? There's that. That's right there. So we're finished with that. We'll just carry that down, click on Analyze, and those will be. So we now moved one more section upstream, right? That's pretty close to 480. Let's lock that down. Let's do one more, and I'll leave it for you guys to. After this, we'll maybe take a short break, and you guys can work through this. So let's do one more cross section. So we're going here to this next one, cross section number 3. So 480 sits between these two guys, right? I want to always bracket it if I can. So I'm going to take this one, copy it, paste it in as my maximum, and then I'm going to look at these two numbers. This 480 sits between here and there. Which one is it closer to? It's closer to that one, isn't it? So instead of just me splitting the difference, making 0.9, I'm going to use some engineering judgment here. I'm going to say I'm going to make it closer to the 0.8. So let's try 0.85. Click on Analyze and see what we get. And look at that, 482. So I've done this before. That's why I knew that it worked. But anyways, we can paste that in there. Run our analysis again. And that's done. Now I'm going to lock it down, and we're finished. We're closed up. So let's assume that's our method 4. Okay, question?
Which one is it plotting? Which of your floodways?
Right, good question. So if I go back in there, under settings, it's plotting profile 2, target number 1.
Okay.
You can change it to whatever you want, but that's one it's plotting.
Okay. So if you like start your initial 3 and one of them's kind of working and the other ones aren't, you could swap that and then look.
Well, as long as you got it in your head, right?
Yeah.
Okay. Right. Okay. So what he's saying is what's plotting this dark blue area here, and you can change that right in this setting here. But it by default plots the first one. Okay. So now we want to go and name this plan. We're going to go over to Input, go to our Scenario Manager, and let's change this name here to our Method 4, right? And I'm going to copy the same label here, Method 4. So it's only the plans that's changing. The geometry is not changing. We're going to leave the geometry alone. The encroachment data is stored in the plan file. So that's our method 4. Of course, I probably want to run our simulation again. Hit the little running person because I've run that simulation. And it ran our simulation for us. Okay. And so next thing I want to do is use my method 1, right? So I want to make a duplicate copy of this plan. So under here, I'm going to say, under here, where is it? Under my input menu, say duplicate current scenario. And we're going to use the same geometry, but we're going to name the plan. We're going to call this method 1. Hit apply. And so it should be referencing our same plan geometry, right? So there's method 1. There's our bridge, and we might want to name it something other than that. If I go over to method 4, it's the same stuff there, right? Okay. So we're in our method 4. We're going to switch over to method 1. Now, right now, it doesn't have any results. If I go to my floodplain encroachments dialog box, because I'm working in a new plan, there's no data. So I have to click on the Analyze button to get my method 4 data back. So we just click on Analyze. It's going to run our simulation again. Now I've got my results. Now I want to take these results and I want to put them into method 1. So we're gonna go ahead and hit the little. Now here you see it's unlocked. If it's locked, it'll complain. But we're going to say copy 4 to 1. It's going to take our results from method 4, duplicate them into method 1. And so now you'll see that these columns become available and this target goes away. So I'm going to say copy 4 to 1. Where it says copy method 4, computer left, right, encroachment station, encroachment method 1 for what? Well, I want to do it for the current and all upstream cross section for all profiles, including any that are locked. Now in this case, there aren't any locked ones because we copied them, but say yes. And notice now my targets are gone. I'm working with method 1 and my encroachment stations. All right. Now in this case, you don't necessarily need to have all your profiles. We're going to have 4 profiles, but you can work with just one of them. So we're going to work on profile, the second row here, target number 1. Now if we go look at our model, we zoom in on it. This one's looking okay. Let's say we've got equal reduction, right? So it's removing this land from the floodplain, and we can develop that property. Same thing over here. This whole area here is developable, right? But let's assume that this is our landowner we're working with. And we can argue now that this encroachment station is tight to that bank. We probably would want to move that away a little bit, just kind of give it a little buffer there. And the same thing here. So we're going to go back into our dialog. You can press Control-R, it repeats your last command. We're going to go ahead and let me lock everything here. We're going to unlock number 2. We're going to go and click on this little button here. The dialog disappears, and it can come in and say, I want my encroachment station to be right there. So notice it puts a little dot there and changes my encroachment station. And I want to do the same thing on the other side. I'm going to pull that a little bit further into the floodway. And there it is. Then I click on Analyze. It's going to rerun my simulation now with my new target encroachment stations. You can see it shifted. And again, I'm still within my 1 foot rise. In this case, it's much less than that. Same thing here. We'll just go and lock this one down. Unlock the next one. We'll hit the little browse button here, little measure button, come in here and say we'll put it in here. And we'll come back over here and we'll put this, let's say, right there. Click on Analyze. And that's in there, and that's all looking good. All right, and now we have a nice uniform floodway through there. Okay. Now, who has done this in HEC-RAS? Is this a little easier?
Yes. You would have saved me like months of my life. Because we're around a couple years ago.
Yeah. Okay. And probably a little bit of hair too, right?
Yeah. I mean, I had like a 700 cross-section model I was doing this for, and it was terrible.
Terrible. Okay. So we also have this in 2D modeling. We're the only people that can do 2D. We worked with AECOM in another office and developed an algorithm for them. And that's not yet available. So I was hoping to demo that for this training course, but I was unavailable. We didn't have it finished enough. But you can do this same analysis with 2D modeling. Okay. So, and again, it's very similar to that.